thanks, Eva. So I met Eva at too many conferences, and does it work? Does it work? Linux and HDMI. Nice. Just turning this down. So, yeah, it's real nice if it would work. Cool. My Linux decides to put the presentation mode on a different slide. Just give. What you have to know is that I'm working on eBPF like on the side, and it's supported by the people that I work with at SAP, where I'm a developer more in the later. Um, and this is like a first draft of this talk, so it's the first time I ever give this talk, ever show this code, so yay for you. Other people pay like thousands of euros to get into there, and you just get it for free. So I'm happy for any criticism later, because I probably give this talk at least like once in the future. So feel free. So anyway, let's check where this works. No, yeah. So it's called sound scheduling. Without further ado, let me start. After Evie took his picture for social media. You probably all know the problem, and it's not a problem that your kitchen doesn't look as clean as this. This is my kitchen. I took this picture on Friday. And the problem is, I sometimes want to make loads of food because I need to. For example, this was me doing food in November. Um, I did I did like 10 focaccias, 7 cakes, and anything. But I had a problem. Um, that wasn't my kitchen. My kitchen was instead this. So when you want to bake that much, you have a problem that you only have one oven, because yes, here I would have had 10 ovens, but sadly it's not my kitchen. My kitchen is far smaller, so I have a problem. I want to do focaccia and cantuccini. Cantuccini are small Italian cakes, cookies, so I want to do lots of these. So assume we're only doing focaccia and cantuccini. What you have to know with cantuccini is that you double bake them. So what you can do, for example, you bake the cantuccini for the first time, you bake your focaccia in the oven, and then your cantuccini again. And this is pretty nice. It works because you have two things that want to run on your oven, and you have one oven, so you need to do scheduling. So you need to do some kind of scheduling, and it's getting more interested if then in the middle of the focaccia a friend comes by and she wants some dessert, and you're like, oh no, I need some homemade biscuit, and then you're like, what do I do? So in a perfect world you could have planned everything in advance before, know this the whole timetable, but the world isn't perfect. Somebody needs dessert, so essentially that's scheduling. And we have the same problems that I showed you here um, in the real world on our laptops. So what is scheduling? It's essentially the same process, just not with cakes, but with processes, and you have multiple CPUs in this system. I have kind of with hyperthreading 16 cores, but of course you can have systems with far less cores. So to simplify it, we have two processes, A and B, and only one CPU. So of course process A could run all the time, but that's not good. Process B could run all the time, but then also process A would be surfing. So essentially what we usually want to do is that we run process A a bit, process B a bit, process A a bit, and so on. And take care that if process B doesn't want to run because it's like sleeping for a minute or something, or waiting for a resource, that we don't waste time waiting till B can run. And can you hear the sound? The cool thing is, that's my scheduler. That's the sound of the scheduler. If I move, it should. If I do something on my laptop, it should modify. Question is, what can I do? I can. That's just the processes. I'll show you later how it works. And if I run something more complicated, like a make build on the OpenJK, I've didn't done it before. Because that's what I do for work, not the sound part, the OpenJK part. Okay, yeah, that's the problem when you do makes and you have done it before. So a make clean. Let's see how it goes. That's the symphony of my laptop doing an OpenJK build. Yeah, you know how it goes. If I remember correctly, minus yacht should. Oh, jobs and. I told you it's a draft talk, so. Yeah. Now it should calm down. Probably some things in the background, you never know. I stop it for now because it can be quite annoying when you're giving a talk besides that. But yeah, that's essentially the sound of scheduling, and I show you in a minute how it works. It's not hard. And of course, it's my scheduler, so I can write it in any language they want. And of course, I write it in Java because otherwise it couldn't be here. If I write it in Go, you would boo me out, and that's you're right. But it's fully written in Java. No single line of C code in this stuff. And you wonder why, and that's why I'm here. And I tell you more because Java is cool. So why? Because I can. Or to quote Clark's second law, the only way of discovering the limits of the possible is to venture a little way past them into the impossible, and that's what I try to do. So why not do kernel programming in Java? And when I gave a talk at the Linux Plumbers conference in September, where like all the Linux maintainers like come together and gave a talk on this, and people asked me whether it was a joke and whether I'm insane, but that's fine. They just don't like Java there, apparently. Why do I like Java? Because it's my job to like Java. I work at Submachine. I have stickers. We're like the third biggest contributor to the OpenJK. So I'm actually working on profiling in the Java world. So fingers crossed you get a new profiler in Java, CPU time profiler in JFR, in hopefully in autumn. And I work in the larger team surrounding is Gardner. We do Kubernetes related stuff, and it's pretty cool. So in the end, how do we implement our scheduler? Or essentially, how do we modify the kernel? In the olden days, you had two traditional ways. You could either change the kernel. That's not that easy. You know there's someone called Linus Torvalds on it, and he probably wouldn't like us to integrate Java in it, and he probably wouldn't like us to change anything in scheduling, and scheduling is really arcane, it's really hard, so that won't be an option. You could also do the kernel module. I don't know, so interfaces are complicated for a kernel, and the kernel module, for one, it's not possible with schedulers, as I see it. But also the problem is that the interface changes quite a lot all the time because, for example, when you see it, you can also use it to modify other stuff. Or when you see the changes that came, for example, from USB 2.0 to USB 3.0 were so massive that it probably changed so many interfaces just because of this. So it's really rubbish. Only write your kernel modules if you're a large company, or if you're a student in his bachelor thesis who wants to really disable CPU caching, and you can disable all the CPU caches on your system if you want to learn more and want to know why it's terrible. Come to me later. Anyway, that's where eBPF comes in. So eBPF is essentially um, a way to hook into your kernel. To quote Brendan Craig, who is seen here shouting at hard drives, eBPF is a crazy technology. It's like putting JavaScript on the Linux kernel, and he likes JavaScript. I know in Java circles, mentioning JavaScript is not the best thing, but that's how it looks like when he's not shouting at hard drives. So the cool thing with eBPF, it essentially allows us to hook into different parts of our Linux kernel. For example, we can hook into all syscalls. We can see later how we can exploit this if you want and do some malicious coding. We can go into the TCP/IP stack. We can go into the whole network stack and do really fast package blocking. And we can, of course, go into the area of monitoring because this code essentially runs in the Linux kernel, and that's pretty cool. So we have access. And how this essentially works, we have on the one hand we have our userland part because that's where we usually develop. And what we have these small programs. You probably all know with when you develop something like Spring that you have like callbacks. That's essentially what you have here. So essentially we take our program written in a magical language, in my case Java. You compile it down and then you have a bytecode. The bytecode is for pretty simple virtual machine that's far less complicated as the Java virtual machine, but it's a register-based virtual machine. And the cool thing is it has so few registers and so few instructions. And you can JIT compile it to essentially any machine. So to the JIT compilers in the Linux kernel built in for all the major platforms like S390 or PowerPC. And of course, smaller platforms like x86. But essentially, you have this bytecode, then what you do, you need to put it into the Linux kernel. Of course, you need root privileges. So if you see me struggling with remembering my password, that's why you see me struggling, because you need the privileges. You can't just run any code in the Linux kernel. That would be pretty awful. And then there's the problem, you probably all know null pointer exceptions. And they are fine in your user application. It crashes, it's fine, but it's not that nice in the Linux kernel. So you probably don't want to have null pointer exceptions there, and you probably don't want to have non-terminating programs there. And that's where the verifier is. Anyone is anyone firm enough in computer science? Are there any problems with like giving guarantees on programs, especially terminations? Any? Yes. Yes, and it's theoretically not possible when you have unbounded loops to prove them. That's the theorem of Rice there. Um, but essentially, we just say, oh, you can just execute like 4 million instructions, and after that, we just say, nope, I can't verify it. And that's pretty cool. The verifier is a really nice piece of tech. And what we then do when the eBPF program is approved, because every time we load it in, the verifier says yay, I check it, and the verify error messages are really well to read. If anyone knows LaTeX, they're like on LaTeX level readability, or C++ for that matter, when you use templates. Because you essentially get like, hey, here's some bytecode and I don't know what to do with it, and here's some cryptic message, and go for it. Especially when you have larger programs, it becomes hard. So essentially, what you do then, you have this bytecode. You usually JIT compile it because we want to have it fast. Because I don't know, we don't want to have a slow scheduler. Kind of. So then what we then do, then we attach it. So we can just tell the kernel, oh, you loaded this program, then you attach it. And there's of course a problem. It's nice that we can have like load our programs and they're essentially like our small things in there. But how do we share data? We usually have two options in normal programs. We can either use sockets. It's like simple WebSockets. We can just send data, or we can use shared memory. That's also possible normally, and we have some synchronization so that we don't have race conditions. But there are problems. We probably don't want to have the message parsing because that's quite with the sockets. It's quite elaborate, and we probably would need to have a protocol, and we also don't want to have shared memory because we don't want to access memory in the Linux kernel from user land without checking. That sounds like recipe for disaster. So essentially, there are eBPF maps, and they allow us to transfer the data in and out. And you heard the noise there, my sound of scheduling. Essentially, that's allowed because my scheduler records this information, and then we get it out. Via maps, and essentially we have so many different maps. We have, for example, um, queues in there. We have hash maps, and that's really cool because we don't have to implement. If any one of you did write C code before and didn't have like a boost library and tried to implement their own hash map, you know that it's not a good idea. And in the Linux kernel, we have pretty decent data structures. For example, also priority queues. They allow us to pretty easily implement schedulers with priority queues, because we just don't care about how they implement it. They usually find the kernel programmers know how to bit fill and optimize. And so essentially the idea is that the maps stand essentially between both, and we can use this to communicate. Then to the end of like the eBPF part, essentially the use case I told you before, like networking, security, observability, and nowadays also scheduling, as I show you in a minute. Then we have eBPF projects that use this, like Katra and Pixie and other tools like Cilium. Essentially the idea was, and that's why where eBPF started, is you have software defined computing with like Docker, and then they want to have software defined networking. And you do this because with eBPF you can go directly into your networking stack and modify it without creating kernel modules. And then there is the case, and then there's the runtime. And of course, there's one missing there. And to quote a famous movie trailer, I want to use a programming language which doesn't only run in userland. So that's what it's there to do, and that's why I'm here. Now back to scheduling, but is there any question regarding eBPF? We're here in an informal setting, so feel free. Anything? Yes.
Who schedules his scheduler?
Ooh, that's interesting. Um, Essentially, we don't have the problem because, and I can show you in a minute. The thing is, how a scheduler works, it works using interrupts. So we essentially have hardware interrupts, so we don't have a problem. So usually, what you have on systems, of course, you have a scheduler that can say, "Oh, please program run," but you can also have POSIX signals, and the kernel uses different things than POSIX signals, but essentially there's built-in hardware into the computer that regularly sends an event in. As far as I understand, I'm no operating system person, despite talking here about scheduling. But yeah, so the schedule doesn't have to schedule itself. It's fairly interesting if you try to implement the scheduling decisions in user land, because then you have the problem is, consider you have a scheduling decision that needs to be resolved. For example, consider you have, for example, in Java, your Java wants to have needs to run the garbage collection, but it needs to run it while doing the scheduling decision. So you need to be sure that your scheduling decisions don't depend on like userland stuff that can potentially cause scheduling decisions, because then you have the circle of doom. So that's the reason why the scheduler runs usually fully in the kernel. There are trials with BPF Rustland, which Andrea Rigi developed, where you can do this, but he instrumented Rust, so it doesn't allocate any memory, and he knows what he's doing. But usually they run in the Linux kernel because there you don't have any problems. And in eBPF, and that's pretty important, you can't allocate new memory. Only on the stack, because any new memory allocation could kind of cause problems, because you could have hit a page fault, and page faults, see someone nodding back there, are not a good idea when you're currently in the scheduling. So when you're currently in the scheduler. Any more questions? Yes.
For later.
Good. Then I'm going back to scheduling. So I also have stickers from ScadeX. That's the 6 support. Uh, don't look it up on Urban Dictionary. It will lead different results. Anyway, that's the project here, and it's the Scala extensions of the Linux kernel. And to quote Dejun, who is one of like the creators of the Scala extensions, the idea is that we want to ease the experimentation and exploration, because with eBPF we can load it at runtime in, and it's even cooler because if my scheduler, for example, here breaks down, then after like at most 30 seconds of not of one process not being scheduled, my Linux system is like, okay, your scheduler is just rubbish. I drop it and go back to a normal scheduler. So even if we do some bugs here, which might happen in a live demo, after 30 seconds the system is again usable, and that's pretty cool. It allows us customization because we can easily write a scheduler that works, as you saw before, that emits sound, because I can, and does other crazy things without having to recompile the whole kernel and learn all about the internals of scheduling. And it allows rapid scheduler deployments, because I talked with someone from MIDI and they were like, yeah, they had like 10,000 machines where they want to test in like a large system, and before they had to reboot every machine, and you know how long it takes to reboot a machine after you recompile a kernel, and then you made a tiny mistake and you have to do it again, and nowadays you can just say, oh, I push it on, essentially via GitOps, and that's pretty cool. For myself, I started looking into Scala extensions in summer, and it's a pretty cool project. And the cool thing is it's based on eBPF, and when we combine this with the Hello eBPF library, and I'll tell you in a minute more about this, which is my Java library for eBPF, we can write our own schedulers in Java. So let's create a scheduler. A scheduler is pretty simple. So how can you create one? You all know Java. Hopefully, does anyone doesn't know Java? Good. That's also fine. If you know eBPF bytecode. No, so it's pretty simple. So what my eBPF library does is it essentially allows you to write eBPF C programs in Java and compile down to C and then later to eBPF. I'm not doing the whole compiling down to eBPF bytecode because this would introduce so many issues and they don't want to debug it. Because the bytecode is not complex, but the problem is because the bytecode is so restricted, you want to have, and you can't, for all the compile nodes here, you can't use that many registers, your stack height is limited, so you need to have some nice optimizations in there to work so that it works properly. That's why I just emit C. But anyway, so what we see here, I'll show you in a live demo in a minute. You see that we annotated because we need to tell the license. All eBPF programs should have a license on there, and usually the license is GPL, because all when you know a little bit about GPL, you know that when you use methods directly programmatically of a GPL license code, you usually have to also tell that it make it GPL licensed, and the scheduling code is such code. And then it's just a class that extends our eBPF program class, and then we just implement scheduler, and that's all. Implement a few methods, and boom, in like 10 lines we have a scheduler. And what's the performance of it? Kinda good. Not as bad as I thought for typical Java. So how does it work? As I told you before, essentially we take our Java code. We have in the Java code our code that's compiled down to C code and a code that runs in userland. Then we compile to eBPF bytecode, load it in, and scale and attach it to a scheduler extensions, and then it goes on. And what you need before we go into the demo, you need to know is that the whole concept of scheduling is the concept of queues. So you have a task and you have a global queue usually in a simplistic scheduler. You have like one queue where you feed in all the incoming processes that say, oh, I want to be rescheduled again, I'm ready. And then what you essentially do, you push them into local queues for every CPU where the CPU takes out the process. And the CPUs can either put it back into a local queue or put it back into the global queue, and you have essentially in SCADX different hooks where you can hook into and say, oh, I want to modify this, or I want to tell you how to implement it, what to do when a process gets ready again, when a process first comes in. And you even have like, because you have ticks with like the hardware interrupts, you can also say, oh, at every tick do something. And I show you quite a few. So that's the sound of scaling. That's slightly more complicated. Let me here. You can't probably read it. Should we make it a little bit bigger? I think Marit likes it when I do presentation. I think presentation mode should work good. So let's see. Let's get minimal scheduler. As you see here, you can also give it a name because then you can later see which scheduler you wrote. That's nice for debugging. We can define simple global simple constants, and then we initialize. So essentially, we create our new queue, and here we create a simple one global queue. And then what we can do, and the cool thing is with Hello eBPF, with my library, I have Java docs for many of the methods, so we can just read it. So what enqueue does, it gets a pointer to the task being enqueued, and then it enqueues the, and then you have to take you have to do something with it. So that's every time a process gets ready and it's like, I want to be scheduled. This is called, and so what we do here, it's a simple scheduler. So we just dispatch it to our global queue. And what the slice is, essentially we tell it, oh, you can maximum run for this amount of time. So a simple first in, first out scheduler would just be like, oh, I just let you run for infinity till you say you want to get off. Any idea why this is terrible? Starvation, yeah. Should we do it? Like, should we just, I don't know whether it works, like make it it's an int. So I think make it like 5 seconds. Let's see. And before we test this, I just tell you more about this below. And the cool thing is, with this setting here, we could just, why not try this in this talk? And so, and then dispatch is essentially a really weirdly named method, and it changed in the recent months. Because this is essentially called by CPU when it's like, oh, I don't know what I do. So essentially it says like, hey, give me some work, please. It's like a busy junior developer when you've worked with junior developers. They're like, I don't know what to do. Please give me work, and you give them from the global queue. And here in this example, it just takes the first. It doesn't have any preference. It's like, just give me anything, and then runs it on and runs it for this amount of time slice. And what's cool with my library is that this whole part runs in the Linux kernel. That's actually run in the kernel. This code is run not in the kernel, of course. That's Java, because essentially what we model here, we can model C code in Java, which sounds weird, which is weird, but is pretty nice, because you can read this as a Java developer, and probably now, especially with like with like annotations here, you probably know what's happening here without having to have a separate C file where you have code in there. And then we have the main method. That's pretty simple. We just load it in the kernel. As I said, we have to load this in. I build a compile plugin that takes care of all the compilations. So essentially, it's built into, when you get a jar out in the end, it's built into this. The bytecode loaded. You just tell, please attach the scheduler, and then you wait. Let's check. So what we done here? What? That's nanoseconds. That should. Oh, good. Yeah, some of the methods aren't documented because it's auto-generated. So you, for the compile nodes in there, you probably know that they're like there's like type information like in the TWAR format, and essentially eBPF uses a version of this and defines all the methods and types, and I use this and generated 15,000 classes out of this that represent all the types in the Linux kernel that are exposed to eBPF, and that's auto-generated. And the cool thing here is it has lots of annotations that do cool stuff because they essentially describe what it needs to do. So it's pretty versatile. But back to this. Let's see whether my system breaks. Can I open a terminal? Oh, okay. Let's see whether it works. So we can compile it. It's simple. You all know the drill. It's main package. It's always the scariest part in a talk, the first demo where you actually want to compile something. Once did a talk in a Python user group in a Python conference where I gave a talk on how to write a debugger. The problem is I had to debug my debugger on stage. Yes. Well, I also debugged the Java debugger, not on stage, but I found the null point exception in the Java debugging agent, which is also real nice. But anyway, it worked, and now you can see how well I remember my password. Run sh minimal scheduler. And the run sh is nothing fancy, it just calls Java, and you need to be aware that I'm using interesting parts of Java, so you need to tell Java, please open a few modules because you should normally not use them. Oh, and it uses, of course, a modern Java version. Just because I'm using, so it's essentially behind the scenes, I'm using, recompiling this again. I'm using the FFI API Panama to call C methods that take like care of many parts of eBPF, and essentially I'm wrapping this in like a nice Java API. So let's see, that works. So after runtime, interesting. This should work. Hey, how did I get this running again? Nope. That's how I got it running. The problem is that when you're in root, you have to pass it the path through because root has a different path. So, good. This should now run the scheduler. What we can do, we can verify that it runs our scheduler by using, where is it? Yeah, by using this here. It's still running our scheduler. Oh, it doesn't break. That's nice. Because I think my system is currently not fully used. What we can do, we can generate some load on this machine because that's just nice. Oh, you see it here? Did you see it? When you generate some load, it's really sluggish, but oh, nice. So I think I created in the samples folder. I created it somewhere. No, we didn't. So essentially, you might assume that this just generates. If you generate some load, oh, we can generate some load. We can just make as before some OpenJDK. Yay. Make. Didn't know that typing make was the hard part. That's why you don't want to use FIFO schedulers. Because it works fine, and it's usually, for example, something like FIFO scheduler is used, for example, if you know the new project Loom with like the virtual threads, that's essentially FIFO scheduler because you can't interrupt them. But here you see that it's gets really. I'm just moving my mouse and nothing happens. But it's I don't know why it now works. So the FIFO scheduler has. Does anyone have an idea why the FIFO scheduler could still be a good scheduler for some use cases? It's really efficient because we let it run. In this case, we let it run for 5 seconds on end, and as someone from the scheduler project told me, like 30 seconds is infinity in scheduling world. So 5% is like 1/6 of infinity, so it's probably still infinity if my math is correct. Um, so it can still have it can still have its merits, and when you have a more decent scheduler, and then let's hope that it has cool parts, killing the scheduler, finding the scheduler here. So yeah, that's so you see it works, but what I instead usually do is I implement something that has a far shorter scheduling slice here in this example 5 milliseconds because this is good enough to give presentations with alongside, and even the demos I did with this scheduler, I did one conference talk in Mainz and it worked, and I showed people that like ta-da, it's running all with this. The idea is that what this scheduler makes a bit better is that you see here that essentially I'm scaling the time slice by the number of or reducing it by the number of currently waiting processes. So essentially, if my system has lots of processes waiting, I'm like, okay, I just slice it. I just reduce the scheduling slice, and that's a fully working scheduler. I don't know, I like it. It took like a year to come to this point, so I'm working now on this project 1 year, and I'm glad that I'm able to work a bit like as my Friday evening, afternoon project at work, and I spent too many weekends on this. And I show you later a link where you can find like my 18 blog posts on this topic that I wrote since beginning of last year. So yeah, it wasn't an easy feat, and I can show you a little bit how this tiny.
Automatically unloads your scheduler when you.
Yeah, sure, sure. Because Java is really nice. Ta-da! What we have here is I can show you how this works. Is that it's just not a classable. That's why we have try with resources. And so let's check. There should be a close method. There's a close method, and this destroys everything. Uh, because otherwise it would be pretty hard to debug this stuff because you're like I used a different library before. I'm now using a model library behind it, but I crashed my system. If you do eBPF programming and install the wrong libraries, you have to reinstall your whole system. So be aware that it's still interesting work, but I wouldn't probably do this thing like you can probably do it, and I do it on like a laptop too, but you want to have a second machine with which to search for the error messages if you get them, and don't autoload anything on startup in a service or something because then you have fun. Anyway, so it's essentially an auto class, and the cool thing is here, how does my library work? It's not so difficult. What I do is I have a template language with which I can just tell, oh, please scheduler interface, you have to preface some code, and you see here I've done all the copying in code for you, and that's all the hooks that I currently support. There are many more hooks. So, for example, the enqueue in this patch you saw when the process gets idle, when a task is initialized. So task and process are kind of the same, but it essentially means like process in Linux kernel speak is like anything that has its own stack essentially. When a process is running, when it's enabled, disabled, when it's stopping, and so on, and that's pretty nice. And what I do here, this is using an annotation processor. That's like the most basic thing. When you do some code modifications, you can just tell it, oh, look for an annotation and do something with it, and that's the reason why you saw the eBPF annotation before. And then I compile a bytecode here. That's just a placeholder here. But then you have here the code, and it's the basic code here. I'll show you in a minute something more interesting. But then I do here lots of things that just help you because you don't have to define it. For example, you can define your data structures when we, for example, have a hash map. I can show you this in a minute. You can define here a BPF map and anything, and I take care of like defining how it works. So what we have here, minimal scheduler. What we then do is we compile this down to C because we need to. That's also why the amount of Java that you can actually write is quite limited, and because in the end I have to just put it into C, and you essentially have these methods. In eBPF, every method has to return something, usually 0 here, and you see here that's the scat init that we saw before. That's our scat enqueue, and I just compile it, and that's how it works. And this took months to get it running, I can tell you. And that's cool because now we have a scheduler. Of course, and I can go back. As you saw, schedulers can be simple. And you saw that it's pretty simple, but they behave differently. Oh, that's what I want to have the demo. Anyway, you saw the demo now, yay. Now in different scheduler because this scheduler is pretty boring because it's nice, it works kinda, but we can use schedulers that we usually don't have on our systems. One of them is the lottery scheduler. Has anyone heard of the lottery scheduler before? Okay. This is a pretty simple scheduler. Essentially, the idea is it's like lottery, or tombola or something. So essentially every task takes a ticket into the bowl, and when task has a higher priority, then we can put multiple entries in the queue, multiple tickets. And then what a scheduler essentially does, every time it randomly picks a ticket and then says, "Oh, you please run." And that has advantages. For example, it's fully randomized, so it's interesting for testing purposes because we cannot depend on like, yeah, this process got scheduled now and our system is busy, so it will be scheduled later, but because it draws randomly, and it's fun to implement. It's of course not really a great scheduler because it takes quite a lot of time for every scheduling decision, and it doesn't take into account what we usually want to take into account, that we want to have these responsive ones. For example, when I jiggle the mouse, they take only a few milliseconds to process versus the large I'm building OpenJDK, which takes quite a long time. So we want to prioritize the short ones. But anyway, the schedule, like having a lottery scheduler, is quite fun because it shows you how versatile it is and how easily we can implement our scheduler. So essentially, we've seen this before. We've seen this before. We extend the BPF program, give it a name, and we create a queue. But the main difference is here that our dispatch contains a loop. So the idea is here, we loop over the whole queue, and we first get a random number. That's like the ticket that we want to pull, and that's here is lottery scalar without any priorities to make it simple. So we get a random number modulo the number of items waiting. So we get a random number in the range between 0 and the amount of things waiting, and then we have here lambdas because that's the newest addition to eBPF to work with, and we essentially just pick it. And of course, there's some processes that can't run on every core, so we just skip them, and we take the next. And that's a simple lottery scheduler, and we can even build schedulers, as you heard before, that can produce sound. And I can restart it, and we can also use it. Just uses MIDI, so the banjo is also quite funny. Think piano, and so what this does is pretty simple. So when we have here the FIFO scheduler and the other schedulers are the same. What we can do in eBPF, as I said, we can before in the beginning we can have hash maps, even hash maps with like least recently used semantics, but we can have hash maps. We give them a size, and we can use them. We can get and put from kernel land in like our eBPF program, and we can do the same in userland, which makes it which allows us to have the task guard, and task guard is just a class that my program takes care of, like transferring it into a kernel and getting out, where we just say, oh, what's the process named, how many times it was dispatched, how many times did it run, and that's all. And then what we do essentially here when we dispatch, we just record it. So where is it? We just get our task guard, and later we record it. And what we record when the process starts running, we get its task guard. It's important that in eBPF we don't have allocated objects on heap. We also don't have any garbage collector, so we can only pass pointers to objects. So we define a pointer here and get the task guard, and then we set it when it starts running. Say hi, yay, you run, and stopping. We also record things. And that's pretty cool because and to access these variables, yeah, we just get a task set and then ask on BPF hash map like give me please all values, and then we can access the task guard object as we want. And then when we do this correctly, we have the scheduler. Told you before. Nope. Should use a simpler password for this. Oh, good. This purchase. I think it's acoustic piano. So how this works is essentially every like 150 milliseconds, it checks the map and it's like, oh, did you run? So how long any process run? Okay. Okay, acoustic grand piano. Of course, it's an acoustic grand piano. I think I dialed it out. Oh. System is quite active. Maybe have some other tasks running alongside. But you essentially can see the different behavior. So every node is mapped. Every node is mapped to processes. You, for example, see here that just by a simple model operation. So node 75 runs quite long. And you see here some of the processes that are running. These are the dispatch processes. So I have lots of stuff going on. You see some pipe wires, some gnomes. I'm X-Well producing many of like the dispatch noise, just the piano. And there should be some process on this system that makes it slow. Let's do the simple thing, kill all Java. Oh, that's interesting. Yeah, the cool thing is, can we do this now? Not in the scheduler, but in a different one. So, the cool thing is, we can modify the schedulers. We can do what we want. We can just say, oh, we don't want to schedule anything. And then gladly our Linux kernel says after 30 seconds, you made something wrong. And we can use different algorithms here, and it allows us to experiment and allows us to learn. And especially in education, it allows us to show people, oh yeah, you can try to have a FIFO scheduler, but you don't want to. Um, And another cool thing about eBPF is, of course, we can have some fun. For example, we can forbid a file. We can forbid files. So you probably know that there's like system calls with which other programs access like file system stuff. And there's the OpenMed2 system call. And so what we can do, we can just implement the system call hooks interface. It's another interface, and what we can do when we enter the system call, so it's essentially every time the system call is called, we get here we get access to the directory file pointer, to the file name, which is like a char pointer, and to like the open how it is like the read write whatever flag that you pass to open. But the cool thing is that file name is like a pointer, so we can modify it. So what we can do, we can sneakily just read it from userland, because we're in kernel land, but we can access with different BPF helper methods also things from userland, and so we can read it, copy it. That's fine. Then I wrote a simple method that's like is file forbidden, like is this file this slash tmp slash forbidden. And if so, what we simply do, we're tracing a bit, so we're seeing some error output, but we're like, we don't like your file name. We just replace it with an empty string. So essentially, how this works is, it's a hook that's called at the beginning of the system call processing. So how this is working is like the Linux kernel only sees an empty file and is like, what? I don't know an empty file that's broken. And so let's hope that it works. Cannot find caused by. If I call it, it's probably it might have been in the demo folder. Yeah. So I just open. Can I split this? Split right. So let's see. Let's just open. Let's just open a normal file. What do I have here? I don't know. Vim slash tmp blah. You can see we can type something in and access it. That works. But what happens? Any guesses what happens when we do this? Kind of, yes. Because Linux kernel is like the file system is like, I don't know such a file, and so we can hide this. Of course, we can use symbolic links, because symbolic links are implemented in our operating system, so this can be prevented with symbolic links. But of course, we can also then, because we have access, we can also say, oh, you want to create a symbolic link, you need to use a system call. Guess who can just hook into this, create a symbolic link system call. And what we can also do is that we can also be, it's very funny, we can do random, let's do some live coding for the frills. Let's do some live coding. Is it alt insert? No. So does anyone know how to? Oh yeah, here override implement methods. Good. We see here that we have a lot of methods available, and what we can also do is we can use the exit open ads, exit open add to system call. Cool. That's essentially called when we return. So what we could do in this case, we could, for example, print it. This could be helpful, or write it in the map. This can be helpful um, to, for security prevention, of course. But what we also could do is we could just look the file up, because now the file is resolved. We get the file pointer. We can look it up. It's a bit more complicated. I've done it before, but not here. We can just use a BPF print. BPFJ. We can just trace print it and something like this. So you see that we can also do it live. And we can do more things. So this time when we return, we do this, and I think we can also override some things here, but I forgot what. So anyway, another cool thing is we can also use this to do some firewalls, as I told you, and we can just say, oh, we implement the XCP hook. That's another hook. That's called whenever package enters, and so we can easily handle a packet and are like, oh, if you, yeah, please drop it. Please drop every third packet, but just saying, oh, if you should drop, please drop it. And you see that this library and eBPF allows you so much versatility, having so much fun with this stuff. I hope you understand now why I really like eBPF. So back to my slides. And that's all, I think. If you want to know more, I'm here for the evening, because I'm all leaving tomorrow morning. My hotel is close by. You can read more on the Discord code, I hope. Just copied it from my Linux Plumbers talk. My project is eBPF. It wouldn't be possible without my team and with people like Dylan Ramaeng from the eBPF community, and of course the Scala extensions. Like, I have stickers of both the Scala extensions and Submachine down there. And yeah, do you have any questions?
I wonder about the attachments.
Yes.
So, from what I've gathered, we use trace points and
Yes.
things to attach it. But what is the actual attachment, and is it prepared for a pointer to our function?
So yeah, so how it works, we use a system call, of course, but essentially how it works, we load a program into the kernel, then we have it, and then we can look around in this program and ask use a system call to be like, oh, now give me the functions defined in there, because we have type informations associated with every program, and then we can tell the kernel, and then with the type information there lies that we know the offset in the program, so we know the instruction offset in our program, and we can use this to get a pointer handle, and then we can tell the kernel, please attach this to that, and that's how it works.
So,
But
these hooks, it's, for example, it expects there to be something, and if there is, go to there.
oh yes, there should be some. I'm not too familiar with this part, but I think there should be some checking code in the Linux kernel. Yes. At every place where you can hook. But what you can also do, there are different kind of hooks. They're like, as you said, they're trace points. There are like the things that I used were like K-probes, and there are things where you can just say, oh, please, at this location in the Linux kernel, thank you. Uh, I believe so. So that's for other people to explain. I'm just a Java developer.
And yet,
No, it's one of the things that people want is one CPU, one scheduler per C groups, and I hope they'll be coming in the future. But essentially, what you can do, you can just implement it yourself because when we go back to the scheduler, when we go yes, and they are different, and they are different, and there are some things that you can do with arenas and such. But as you see here, um, you have the CPU already, so you know it, and you then just use a different algorithm. So, but be aware that programs can't be too big because, of course, we have the verify limits and everything. So it gets complicated when the program gets large. But there are tricks around it. Uh, but of course, there are always tricks, but they make it even more hard. Any more?
Do you have any custom eBPF modules that you are using in practice daily, on a daily basis?
No, because if I'm honest, that's just like a project where I learn eBPF. But what I want to do, and I need to prepare a talk till in 2 weeks because I'm giving a first time talk, is that uh, what you of course can do when you have your custom scheduler, you can tell it to please not schedule this certain process. So what I implemented, and I can show you is the task control project that should be here. Oh, that's why it was so sluggish because I was building OpenJK all the time. Interesting. That explains quite a lot. So, essentially, here's the task control. I hope I have a picture in there. Um, essentially, what the idea is here that my scheduler gets a web interface because so and gets a web interface. I think I wrote it with Java or something. Please don't expose this to the internet. It's a major security risk. Um, and please, yeah, only on localhost and only do it on your test systems. Please not in production. So the idea is here that you make it a little bit larger. That it allow okay, that you essentially can um, that you essentially can tell the scheduler to please, hey, don't schedule this task currently, or like, hey, I have a scheduling plan, like, don't schedule this like for 10 seconds and then allow it to be scheduled for 10 more seconds. And what you can do is, I hope, to do concurrency testing with it because we're controlling the scheduler. We can randomize the scheduling order and produce really weird scheduling orders. For example, when you have a producer and a consumer, and you just tell your producer like, "Hey, produce for 30 seconds." You'll be scheduled for 30 seconds, but the other task isn't scheduled like for 10 seconds. Do any buffers overrun so you can stress test and generate scenarios which are usually hard to generate. And with this task control, there's also of course a blog post on this. What you can do is um, I wrote some code around it, so you can essentially um, tell the thread control, please, please just stop this thread and just pass the thread, and I deal with everything. So that's something that I want to use in the future to work on OpenJDK to just create, or not in the future, but in the next 2 weeks to work on OpenJDK to fuzz things because a program can't detect it because we're running not with signals which it can potentially detect, but it's like under the hood. So that's one of the aims. Any more questions? Anyway, yes. Yes, I think I have. I think with Java 21, the FFI API was in preview, so I think I dropped it because there were slight modifications. I had a version that worked on Java 1 on Java 21, but the problem is there were some slight unobnoxious but not great modifications of like the Panama API. Yeah, so that's the reason why it works currently on JDK 22 and 23, but JDK 25 will be out in summer anyway. So it's bleeding edge anyway. So I decided I just go for the lightest and greatest, and I've programmed before because of backwards compatibility a lot of Java 8, and I was pretty happy to program in Java 23. That's nice, especially the var keyword saves a lot of time. And Panama is a really nice API. It wouldn't be possible without Panama because it essentially allows us to call down. And the cool thing is, I'm using it all the time, so I'm not implementing all of these attachment because we had it about the attachment when we look here. You see that I'm calling back, for example, to destroy or to attach or to detach. I'm calling directly into a library generated by extract by the Panama tooling, and that allowed it because before Panama it wouldn't have been possible in this short of time to implement this. So yeah, Java is evolving. Keep using Java, and sometimes, and you can even write your C programs in Java because why not? And anyone more? Or should we go? Yeah, I'm the whole evening there, so you just ask me random questions. I want to say thank you to Eva. So I had a random idea to, hey, I'll be traveling through Malmo anyway. Can I give this talk? And he said, yes, that's cool. That's why I'm here. And thank you to Foo Café for hosting us. And have a good night.